So good afternoon, everyone, and thank you for joining this session. My name is Léo Bellali, and today I'm very excited to walk you through a topic that is becoming central in modern embedded systems, which is how we can build security architectures that remain trustworthy all the way from the firmware to the cloud, and that stay consistent in a world transitioning to post-quantum cryptography. Over the next 20 minutes, we will explore how PQC impacts designs, how it impacts security lifecycle, and how organizations like ours at Securizer, now Cadence company, support this transition across hardware, software, and long-term device management. So a quick word about myself. I've been supporting Securizy's customers as field application engineer since early 2024 across domains, including automotive, IoT, defense, and semiconductors. My academic background is in intelligent system engineering at Sorbonne University, and my role now sits at the security customer requirements and practical deployment constraints. This presentation we'll have now reflects the type of discussions I have every day with OEMs, chip makers, and system designers who are preparing for the PQC transition. So here's the agenda for today. We will start with a short reminder of what post-quantum cryptography is, and more importantly, why the transitions matters now before a quantum computer emerges. From here, we will deep dive into the core of this session, which is how to build PQC-consistent architectures starting from the design phase, and how to maintain this trust across the entire project lifecycle. And finally, we will close with a few takeaways. Okay, so let's begin with a few words about Securizy. So here at Securizy, we are a global leader in embedded security. This means we provide solutions that protect embedded systems in all their forms. Our offering ranges from small hardware IP blocks, implementing specific algorithms to complete secure enclaves, to equipment for simulation and evaluation of security implementations, and even expert guidance to support our customers. Our philosophy is to address every security challenges across the entire product lifecycle, from the security design to the robustness evaluation, all the way to helping our customers achieving certification for their end devices. So here is a quick recap of our history. As you can see, Securizy is a relatively young company. It was founded in 2010 and has grown very quickly, opening offices around the world. You will see our global footprints on the next slide. Many of you may already know this, but we are now part of the Cadence group. We have become Cadence dedicated cybersecurity entity. That said, we remain a standalone company. We keep our identity, our DNA, and our mission. The main difference is really a change of scale, meaning that we are moving from a company of about 150 employees to a group of 11,000 people, if I'm not mistaken. And over the years, we have delivered more than 1 billion integrated IPs worldwide, developed over 250 patents, and supported hundreds of projects across almost every vertical: IoT, automotive, industry systems, mobile, and defense. So moving on to the next slide. Here you can see an overview of our global presence. Our HQ is located in Rennes, as you can see on this map, which is also our main research and development center. It hosts about 80% of Securicy's workforce. And in addition to that, we have several offices around the world, primarily dedicated to sales and customer support. And these offices are located in Paris, United States, Morocco, Belgium, China, Japan, Singapore, and Taiwan, finally. A few words about Securicy's portfolio. Here you can see our product tree. As you can tell, it is divided in three main business line branches, which together allows to address all the security challenges I've mentioned earlier. The first branch is Securizer that contains all the security IPs, ranging from the small hardware designs implementing specific algorithms that we call crypto solution, which are bundled to include several IP blocks along with all the software needed to operate them. At the top of this branch, we also offer complete security enclaves, which handle all the cryptographic functions for an embedded system, including secure boot and much more. The second branch is Laborizer, which provides a three-level of solution to evaluate and help certify cryptographic implementation, whether at the pre-silicon stage, the software level, and post-silicon phase. And finally, we have the Expertisizer branch, which deliver our expertise services supporting customers through certification and their certification of their final products, performing full security analysis and providing tailored guidance. As you can see, we have invested heavily in post-quantum cryptography to make it available all our product lines. And now that this is said, let's move to the heart of this presentation. So these slides illustrate the contrasts between classical cryptography and post-quantum cryptography. Classical cryptography relies on problems such as factoring, discrete logarithms, and elliptic curves, all of which are vulnerable to quantum attacks, where PQC, on the other hand, is built on hard mathematical problems that remains resistant even to quantum computers. For example, we have structured lattice. And it is also important to highlight that PQC algorithm runs on classical processor. So this means we can integrate them in today's hardware platforms without requiring heavy or specialized hardware capabilities. Let's move to the next one. Now that this is said, PQC is no longer science fiction. It is already standardized. This timeline shows the NIST certification process that began in 2017, with 82 candidates, as you can see, and led to the publication of 3 new standards last year in 2024. So ML-KEM, ML-DSA, and SLH-DSA. Beyond NIST, we see strong global alignments. Japan, Europe, and national cybersecurity agencies, such as ANSI in France, are publishing for quantum resilient cryptography and providing migration frameworks. What this means for designers is that PQC is now entering product requirements, certification schemes, product guidelines, and even legislation. At Securicy, we have monitored this timeline very closely and continuously adapt our roadmap to follow the standardization process, integrating every milestone of the NIST to ensure we are always ready ahead of time. One of the most important achievements for us is that Securicy is the first worldwide IP vendor to receive hardware CAVP certification for PQC algorithm, especially for ML-KEM and ML-DSA. This matters for one main reason. CAVP is the official validation methodology used by NIST and by certification schemes like FIPS, for example. And it is also important to highlight that PQC is now entering product requirements, certification schemes, product guidelines, and even legislation. At Securicy, we have monitored this timeline very closely and continuously adapt our roadmap to follow the standardization process, integrating every milestone of the NIST to ensure we are always ready ahead of time. One of the most important achievements for us is that Securicy is the first worldwide IP vendor to receive hardware CAVP certification for PQC algorithm, especially for ML-KEM and ML-DSA. This matters for one main reason. CAVP is the official validation methodology used by NIST and by certification schemes like FIPS, for example. And having a PQC algorithm validated ensures that implementations match the exact specifications, which is critical for interoperability and long-term stability. If we take a step back, we can clearly see the global market trends, government organization, especially the CNSA in the United States, play a major role in driving PQC adoption worldwide. For example, the CNSA, which define requirements for the US market, states that after 2030, PQC will be mandatory for firmware signatures, mechanism, and networking equipment, and that classical cryptography may no longer be used in this area. And by 2033, PQC must be fully deployed across all remaining domains that still rely on classical algorithm. The objective is therefore to prepare now for this transition so that designers and manufacturers are ready when these hard stop for classical cryptography will become effective. Let's move to one of the key messages of today's talk. PQC is not just algorithm upgrade, let's say. It's a crucial requirement that every stage of a product lifecycle, it must be present at to design, to manufacturing, to board assembly, until onboarding and provisioning, during in-mission operation in the field, and all the way until decommissioning. And this is why Secure-IC approaches PQC as a continuum, let's say. Instead of thinking about chip-level IPs, we think about the entire value chain, which provide hardware out of trust solutions, secure manufacturing and provisioning technologies, lifecycle management services through our Securizer server platforms, and monitoring capabilities that collect device health and security metrics. And all these elements form a coherent foundation that ensures that PQC can be introduced cleanly, maintained reliably, and updated securely. Now we arrive to the core of this presentation, which is how to build PQC consistent architecture. So the key word here is consistent. Many companies ask us, can we just swap our ECC engine to a PQC one? And the answer is not really. The foundation of a PQC consistent system begins at the design phase, which is what we call the root of trust, or ROT. At Secure-IC, we have developed a versatile core platform called the NeoCore platform, which provides the root of trust for any end product. We offer this platform across 3 different verticals, allowing us to address the specific needs of each market. And this root of trust includes secure boot engines, key storage and key management mechanisms, hardware accelerators for both classical and PQC algorithm, secure update capabilities, and finally, anti-tampering sensors. And in other words, it provides everything needed to ensure PQC readiness at the very root of the device. Moving on to the next slide. These slides show the block diagram of our NeoCore platform, Secure Enclave. This Secure Enclave provides the PQC algorithm required by the secure boot process and by the host system services. This algorithm available here includes ML-KEM, as known as Kyber, ML-DSA, or Dilithium, XMSS, LMS, and SLH-DSA. This allows any end product to be fully post-quantum resilient while performing its mission on the field. So on one hand, we can integrate PQC natively into the chip design, but on the other hand, we must also ensure the migration remains as smooth as possible. and that when one part of the system transitions to PQC, it stays compatible with the other components and it interact with. And this is where cryptography comes into play. For cryptography to be truly adopted, it must remain aligned with the market requirement, the ones you see here, ensuring that cipher suits remains valid throughout the entire product's lifetime, maintaining compliance with the regulation and certification schemes, enabling software updates on devices, and keeping good performance levels, and to preserve both quality and compliance across the full lifecycle of a product. Secure-IC defines 4 pillars of cryptography, which are enabling or disabling algorithm over time, providing hardware blocks capable of supporting future PQC variants, ensuring update capabilities while the devices are deployed in the field. And finally, guaranteeing that the systems has the resources to support those potential future updates. Up to now, we have focused on the most important phase, the one where PQC starts, the design phase. But as we mentioned earlier, PQC forces us to rethink the entire product lifecycle. And in practice, once the devices leaves the factory, the most of the critical security events occur after the deployment. So now that we have seen how to enable PQC at the root of the chip, we also need to maintain this trust throughout the entire product lifecycle. And to support this lifecycle management, Secure-IC provides the Securizer server solution, a cloud-ready backend, let's say, platform that manages all security services across large fleet of devices. It interacts directly and continuously with our ISE, following it at every stage of its lifecycle. It enables, among other things, managing each device's unique identity, providing key during manufacturing, performing secure updates, for example, transitioning a device from a classical algorithm to a PQC algorithm, and finally ensuring secure monitoring so that every device in the fleet remains trustworthy and continues to fulfill its mission. This platform is PQC ready, as we said, meaning it includes every required to maintain long-term trust between a chip maker and its deployed devices. In other words, even if cryptography evolves in 5 or 10 years, this solution ensures you remain aligned with the root of trust architectures deployed across your device fleet. This slide breaks down the server-side services in more details and show how trust is maintained throughout the entire product lifecycle using 4 levels, let's say. The first one is secure device identity management. Each device has a unique hardware-rooted identity generated by a physical unclonable function, which we call PUF. And this identity contains the ART ID and acts as universally unique identifier, and it allows the server to authenticate devices, issue credentials, and maintain trust relationship across the entire fleet. The second level is the secure update service. With this server, firmware packages can be imported, signed, validated, stored, and through a secure pipeline. And this ensures that updates, whether classical or PQC, always come from an authenticated source and cannot be tampered. In third, we have the secure provisioning service. The server enables key provisioning, asset injection, PKI management, and synchronization with manufacturing lines. And finally, security monitoring. The system collects runtime data, diagnostics, tamper events, hit status, intrusion attempts, and performance log. This makes it possible to detect anomalies, enforce compliance, and support proactive threat migration. And together, these four pillars provide a complete end-to-end lifecycle security model from the chip to field operation to the cloud. Moving on to the next one. So let's take a moment to wrap up. PQC is not just cryptographic updates, it is a structural shift in how we design, deploy, and maintain secure embedded systems. To succeed in the transition, vendors need hardware architectures that support PQC without compromising performance, a root of trust that enables crypto agility, secure provisioning and update mechanisms, and cloud-based lifecycle management to ensure these remain trusted for years. And Secure-IC delivers all these layers in a current integrated approach from firmware to hardware to cloud and across the entire lifecycle. The final slide summarizes our positioning, which is the end-to-end expertise. From one unique platform, we provide a complete spectrum of security services. Two, one-stop shop, hardware IPs, root of trust, provisioning, monitoring, everything is delivered in a unified and consistent way. Three, pioneer in PQC, with our CAVP hardware certification and an advanced PQC portfolio. We are ahead of the curve, let's say. For data-driven, we correlate security data from sensors, host statute, and intrusion detection systems to enhance monitoring and threat detection. And finally, interoperable. Our platform integrates seamlessly with existing IoT and cloud infrastructures. So finally, this coherence is what enables customers to adapt PQC smoothly without fragmentation or architectural inconsistencies, let's say. And with that, I would like to thank you for your attention. If you want to stay updated on our work in PQC, embedded security, or lifecycle management, feel free to follow Secure-IC updates on LinkedIn or social platforms, and we will be happy to take any questions. Thank you.